and kind of show you where I want to start. And we should have time to do lots and lots of stuff on here then. Okay, I'm going to go back to the integrals. So let's go to, I think I'm going to start kind of with number 12, just to start with. Then we'll go ahead and maybe do some of the indefinite integrals, but I want to kind of go back and have time to get through lots of stuff here. Okay, so this is one thing I want you to know how to do. Just kind of one problem like this, and it's a no calculator test, so I'm trying to make this pretty simple with arithmetic, no decimals and stuff like this. This one is one where you're going to find the area under the curve of this basic function. You're going from, let's see, where does it say on here? 4 subintervals. So that means we're going to make 4 rectangles. So we're going to have 4 rectangles. You are going to use midpoints. We have that. And then you're going from 0 to 8. Okay? Now my diagram, you can see if you have enough room to draw a good diagram. I'm going to have to zoom on this a little bit so I can see it, and then you can see it a little bit better. If you need to draw something a little bit different, you can, okay? So the first thing that we want to do on this really is we want to draw the graph, okay? Now I'm giving simple graphs. A parabola is a good example. Most of what this is it's helping you understand what integrals are, what finding an area under a curve is. So whatever I give you is fairly simple. You can make a table of values out on this if you want to, and that's what I'd recommend that you do. So first of all, we're going from 0 to 8, and I'm saying take 4 subintervals. So you basically have 0 to 8. What you always do is you say 8 minus 0, and you divide by the number of subintervals. Now, you can do this in your head. You don't have to use that formula. All that means is you're going to have 8 over 4. Every time you have 2 notches going by, you're going to have a rectangle, right? You're going to have 1, 2, 3, 4 rectangles. 4 subintervals, okay? That's kind of, I'm not going to have you do more than 4. It's going to be 3 or 4. That's about it, okay? Because it gets a little bit tedious when you do that. So the first thing that you want to do on this is let's go ahead and graph this, and let's make it accurate. You're not going to be allowed to use your calculator. So, again, fairly simple functions. Just start at 0, okay, like that, and evaluate it. So you're going to have 0 squared minus 2. That's going to be negative 2. Go on to 2 if you want to. So 2 squared minus 2 is going to be 4 minus 2, so that's 2. Go to 4. 4 squared minus 2 is going to be 16 minus 2, so that's going to be 14. Move on to 6. So that's going to be 6 squared minus 2, so that's 36 minus 2. That's 34. And then go to 8. So again, you're plugging in, and you're going to have 8 squared minus 2, so that's 64 minus 2. So that's going to be 62. Okay, and it's important that you're accurate on this thing, okay? So we want to go ahead and plot those points to get our graph constructed. That's why I made the graph, kind of scaled it the way that I did, like that, okay? So now go ahead and just plot your points. So we have 0, negative 2 down here somewhere, so you probably just need to go down a couple of notches, okay? Let's just say that's negative 2 like that. Okay, so we're going to end up having a point 0, negative 2. Then we're going to have a point 2, 2. So I'm going to do that. I'm going to have a point 4, 14. So over 4, up 14. And then 6, 34. You don't have to have this perfect. You're trying to get a visual picture. Then you're doing 8, and that was 62. So you kind of got that. Get yourself a rough picture. Okay? Now let's go ahead and connect the dots. Now like that. We got a parabola that's been shifted down 2 units. That's the graph of x, f of x equals x squared minus 2. Okay? All right. So far so good? Okay? This is a pretty good example because the arithmetic's not hard. You'll see something kind of like that. Now what you want to do next is you want to set up your rectangles. Now what I'm saying is midpoints. So what you want to kind of do on this is you're going to have a rectangle with every 2 units you're going to have a rectangle. But what you want to do is the height of the rectangle needs to be at a midpoint. So put a little dot there like that and then draw your rectangle around the midpoint. Remember we did like left and we did right. Generally I like to do midpoints because it's more what the Riemann sum integral is doing. Okay, so we're going to do that, all right? And it's always a good idea as you're doing these problems to label stuff. That has an x value of what? If it's the midpoint, what is it? It's 3, right? Okay, it's no longer, that's going to be at the midpoint, 3, and then we'll figure out that y value in just a minute, okay? Now, the next rectangle between 4 and 6, go to the midpoint, which is 5, go straight up, put a dot, and kind of draw and sketch in your rectangles like that. Okay, then let's label that as 5 something, like that. Okay, working with midpoints. Okay, between 6 and 8, halfway between 6 and 8 is 7. So go up, just to get a good visual picture of this. Then go to your midpoint like this. Okay, and then label that as 7 comma something. Okay, you guys see what I'm doing? That's midpoints. If I said left endpoints, then you just would go to like 4 would be the height, 6 would be the height, and so forth. What I'm focusing on is midpoints. Okay. Then that leaves you to go in with this one. Halfway between 0 and 1 is 0 and 2 is going to be 1. So you're going to go to that midpoint, put a dot on your function there, and then you're going to draw that around like that, and then that point is going to be 1 comma something. Okay. All right, okay so far, tell me. Okay, now what we need to do is we need to find these y values. Okay, when we do these y values, we're just going to evaluate the function. Okay, our function is x squared minus 2. So what you need to do is just plug in these x values. So you want to do like f of 1, we're going to work out f of 1, f of 3, f of 5, and f of 7. It's arithmetic. Once you get the setup done on this problem, it's all an arithmetic problem. Okay, so f of 1, what do? You go 1 squared minus 2, so that's negative 1. So let's fill that point in now as having a y value negative 1. And it looks right, doesn't it? Okay, it's down below the x-axis. Okay, go to f of 3. f of 3 is going to be 3 squared minus 2. That's 9 minus 2, so that is 7. That looks right. F of 5 is going to be 5 to the second minus 2. 25 minus 2 is 23, so we fill that in. Okay, and then the last one, f of 7, is 7 squared minus 2. That's 49 minus 2, so that's going to be 47. Okay, now I'm ready to finish it up, and it's very simple to finish up. Okay, so let's see if you've got any questions about what I've done. Is everything good? Okay. Now, let's just do our areas of our rectangles. Okay, we're going to say area of the first rectangle, area of the second, area of the third, area of the fourth. How do you find the area of a rectangle? Base times height. Okay, so let's take this, let's start with the last rectangle. I'll do this kind of backwards for some reason. I like to look at that. Okay, what is the base of this rectangle that I just shaded? 2, yeah, okay. So we got 2, base times height. What is the height? 47, that's why we did that. So we do 2 times 47, okay, right? Now when you go to the next one, once you see the pattern, it's easy, okay? The next rectangle, this one, we'll call that one A4, this one A3, so its base is 2 again. What's the height of A3? 23. And so forth. A2 is going to be this rectangle. Its base is 2. Its height is 7. Okay, then when you go to A1, which is this little rectangle right here, its base is 2. We've got to have a times there. That's 2 times the function value is negative 1. You got that? Okay? Now it's just a boring arithmetic problem to finish it up. Okay? So that means you have negative 2 here. Let's see, 2 times 7 is 14. 2 times 3 is 46. 47 times 2 is going to be 94. Then you add them all up to get your final answer, okay? And just add it up in a column if you want to. So 94, 46, and 14 is going to be 10 plus 4 is 14. Carry that. That's 10, 15. So it looks like you have 154 is what those add up to. Minus 2 would give a final answer of 152, assuming I got all my arithmetic done. Okay? It's a tedious problem. That's something I give on the final because I want you to know what we're talking about, a Riemann sum. This is how we develop the idea of an integral. Remember, an integral, you're just making the rectangle's base go to 0. You're taking a limit and making that base go to 0. That's not too bad. That doesn't have too bad of arithmetic. You're not going to see anything with crazy stuff on it. A parabola, something like that, is probably one of the best things to check students on. In fact, that's what I almost always do for a test because it's pretty simple. Okay, so everybody okay with that? Okay, all right. Now, let's bypass the integrals for a few minutes here because that's the last thing we've done. And let's go to L'Hopital. On your last test, there were some issues. There was a certain kind of problem that was very easy for you. Okay. Now, what I'm doing on L'Hopital, this is all I'm checking you on, is 0 over 0 and infinity over infinity. Okay, that's it. Okay. There were other things we did that were more complicated, like the 1 to infinity, the infinity minus infinity. There was lots of different forms. This is what I'm checking you on. Now, the way I do this is I usually just have you tell me what form it is. So on this particular problem, does that say 1? I can't see that very good.
Yeah.
Okay. It's got to be. That's what that is. So let's do 1 to the third minus 10 times 1 squared plus 9 over 1 minus 1. Now, all you've got to see on that is that works out to be 0 over 0. So that means we have a 0 over 0 form. So then what does L'Hopital's rule tell you to do? Derivative top, derivative of bottom, try again. If it's still a 0 over 0, you do it again. Okay, and so forth. All right, so what we're going to do on L'Hopital's rule is we're going to, first of all, you can do this derivative in your head pretty easily. So go ahead and just do the derivative of the top, which is going to be 3x to the second minus 20x. Derivative of bottom is going to be 1. Okay, so this one's going to work out. Okay, now you're ready to evaluate. So you're going to have 3 times 1 to the second minus 20 times 1 over 1. So that looks like 3 minus 20 over 1. So that looks to work out to be negative 17. To me, that's the standard, most basic L'Hopital rule thing you can see. Polynomials, students usually have very little trouble with that. Okay. All right, the next one's probably a little harder, so let's see what's going on this one then. So first of all, you want to just plug in, replace the top and bottom with 0. So you have 0 over sine 0. What's the sine of 0? 0. So it looks like you have that 0 over 0 form. Okay, that's what tells you that you can use L'Hopital's rule. You can't. A lot of times students see a limit and they immediately go L'Hopital it. Okay, you got to make sure that you can L'Hopital it. Okay, I don't even know if that's a word. I just invented it. So anyway, we're going to go through and do that. Now what we're going to try to do is we're just going to do the derivative of this and see what happens. This one probably works out pretty well. All right, so this one we're going to just do derivative of top, which is 1. Derivative of bottom is cosine of x, like that. Okay, now we just reevaluate it and see what we get. So we get 1 over cosine of 0. Cosine of 0, remember you're on the unit circle, you're at the point 1, 0, so what's cosine of 0? 1 over 1 is 1. That actually turned out easier. I was thinking there was something more complicated on that one. Okay, I think I put a couple of basic ones and then one that's a little bit harder to do. I think the number 19 is a little bit harder. Okay, now this particular problem right here, this is saying that you have a limit as x goes to infinity. Now, you don't have to show any work necessarily to get the form, but if you replaced all of these x's with infinitely big numbers, what would you get? an infinitely big denominator and an infinitely big numerator. So this one is the infinity over infinity form of L'Hopital's rule. Now, does anybody just know what the answer to this problem is like that? I know what the answer is in 1 second. Do you? I'm curious. Yeah, good. How do you know? That's a horizontal asymptote. And one thing you learned in college algebra is the degree of the top is less than the degree of the bottom, so the horizontal asymptote's y equals 0. Okay? That's a good thing to know. Let's go ahead and do the L'Hopital on here and see what happens. Okay, so let's do the derivative of the top. So that's going to be 2x plus 8 over 3x squared plus 8x. Okay? Now again, you got to look at it again. If you replaced the denominator with infinity, you would still have something infinitely big, right? Same thing with the numerator. 2 times an infinitely big number plus 8, it's still infinity over infinity, right? So that means we need to do the L'Hopital one more time and see what happens. Okay, so let's go limit. X goes to infinity. The derivative of the numerator is 2. Derivative of denominator is 6x plus 8. Okay, now we're in business. I think we can do it. Now what would happen is if you replace x with something infinitely big, you would have 2 over infinity. If you take 2 divided by an infinitely big number, where do you go?
0.
You go to 0. Okay, so that means the answer to the problem would be 0 because that approaches 0. Okay, any constant number divided by something infinitely big is going to go to 0. Okay, that's an example of something where you had to do L'Hopital's rule 2 times. Okay. Okay, so those 2 examples were probably not very hard. What do you think? Okay, I'm kind of doing that level and then probably one other level. I'm just checking you on 0 over 0 and infinity over infinity. Okay, so this one right here, if you plug this in at the beginning, now this one is going to kind of give you this type of thing. I guess this is a different form, but I want you to be able to do this one. Okay, so this one is infinity, and then you're doing the sign, and see if that's infinity. What's 5 over infinity? That's 0. And what's sine of 0? Okay, so I lied. We're going to do the infinity times 0 also. This one's not too bad. Okay, really, this one's not too bad. Okay, so what you try to do on this one is, if you have something like this, you have to turn it into either an infinity over infinity or a 0 over 0. You have to do that, and you have to be kind of clever about how you do this. There's a couple of thoughts that I have on this initially. One thing that you can do is you can try this. We can go limit as x goes to infinity and leave the sign alone and take this thing and write it as 1 over x. Let's pause over there and see if you understand what I just did. Okay, because when you divide by 1 over x, what are you really doing? You're multiplying by x. So I have not changed the problem, right? Okay. Some of you may be thinking, well, maybe I could change the sign to put it down in the denominator and make it into a cosecant. That might work also. Okay, you could try that if you wanted to. To me, it's just as easy to do it this way. So now what you have is if x is infinity, the form you have is you have the sign of 0, and then 1 over infinity goes to 0. So you do have a 0 over 0 form, okay, like that, okay? So that means we can do L'Hopital's rule based on how we rewrote that function. Does that make sense? Okay. All right, so let's go ahead. Before we do the derivative on this, let's write this as limit as x goes to infinity. Sine of, I'm going to write that as 5x to the negative 1 because I'm going to have to use a chain rule on that. And then x to the negative 1 like that. Okay, just get ready to differentiate. Let's take our derivative and let's see what happens. Okay. All right, so by L'Hopital's rule, okay, the derivative of the sign is the cosine of whatever, but then what do you got to do? You got to multiply, chain rule. So you got to do the derivative of this thing, so that's going to be times negative 5 x to the negative 2 like that, okay? Then you got your denominator, which is going to be negative 1 x to the minus 2 like that. Okay, that's my derivative. Now what you need to do is see, is there anything you can simplify? Does anything jump out at you? How about those x to the negative 2's? See, it's all multiplication, so those things cross out. You can wipe them out and you can do it now. Okay, those go away. So then what you would have is you would have the cosine. And actually, let's bring that -1 in front. And actually, you see you got these two negatives. So those are going to divide out to make a positive 5. Then you have the cosine of 5x to the -1 like that. That's what you end up with. Now we're going to see if we can reevaluate this and see what we get then. Okay? All right, does that make sense so far? Okay, a little bit more complicated, and you're going to have to simplify that. Now what I'm going to do is change this to 5 cosine, take that back to 5 over x. And then we're going to evaluate the limit as x goes to infinity, and let's see what happens. So you're going to have 5 cosine. 5 over infinity is going to go where?
0.
To 0. So you got 5 cosine 0. What's the cosine of 0? So the answer appears to be 5. Okay, that's kind of what you we'll see. There's kind of the basics, and then one that's a little bit more challenging like that. Now I'm not doing the one where you had to do an ln of both sides, where you had 0 to the 0 like that. Yeah.
What happened with the negative when you crossed out the x squared?
Okay, these two negatives right here
that's right.
divided out. That just became positive 5. And say I crossed out the x squared, and then I have -5 over -1 is just 5, like that. Okay, so there's a little arithmetic details. Okay. Okay. Any questions about L'Hopital? So let's move on. We'll do a few more, then we'll do a little short break here. Okay, let's see. Let's do one of the, I guess on the optimization, I want you to know one optimization, and I'm trying to come up with things that are fairly straightforward. So let's do this one and kind of set this up, and then that 21. This is what I'm looking at. The last exam you did related rates. I don't do related rates on the final. You did the one with the box and the volume. I don't do that because I feel like you need a calculator for that usually to do that. Okay, so I'm looking at fairly straightforward things for optimization. Changing these in different ways. This is kind of a classic basic optimization problem to have students do. So we did have done some stuff like this in our homework. So you have 64 feet of fence, and you're going to try to find whatever, let's see, there's the question down here. So you're making the area as large as possible. So what you're doing is you're maximizing the area. So what you ultimately have to do, if you're maximizing area is just, length times width. So ultimately we have to build a function around the idea length times width, write it in one variable, then differentiate it, work with the derivative. So you just got to set this up, and there's more than one way to set this up. What I'm going to do is just put x, all of these things are the same. All right, and since the barn is a boundary, you don't have to do anything there, okay? And then you can do your second variable here, y, and y. You're making the assumption that they're all the same. Okay, I think the problem probably, they're identical pins. Okay, so it does say that. Okay, now, how do you build that using 64 feet of fence? Well, what you do is add all that up. Okay, so you say 4x plus 3y is equal to 64. Okay, that's the mathematical relationship that you have. Now remember, ultimately what you're going to do, you're not going to do the derivative of that because you're trying to maximize the area. So you want to do the area, which if the area in this problem, what would it be? Base times height, right? What's the base of the way I set it up anyway? 3y, right? What's the height? X. Okay, so we got that. So when you do that area, you're going to have to do 3xy. The problem is we have two unknowns. So that base is all of those y's. The height is just x. Okay, so what I'm going to do is I'm going to take this equation, solve it for y, and plug it in. That way I only have one equation. And it's up to you. You can either solve for x or y. It doesn't matter. You'll get the same result anyway. So I'm going to do this and get 3y equals 64 minus 4x. Then I can divide by 3. Okay, like that. So that's going to end up giving y is equal to 64 thirds minus 4/3 x like that. And don't freak out about the fractions. Everything works out beautifully in this problem, I'm pretty sure. Okay, so what do I do with this? That thing is going to plug in there. Now we have a function that we're ready to do calculus on. Okay, so what you would end up having is you would have the area of x. X is our function. We're going to have 3, replace the y with what I circled here. So that's 64/3 minus 4/3 x. And then you got that times x like that. So 3yx. I've got 3yx. Okay. That's going to cross out all these 3's. Okay. If you do a distributive property and cross those out, you're going to get 64 minus 4x times x, because you can cancel out those 3's. Then when you do a distributive property, that's going to be 64x minus 4x to the second like that. Okay? Okay? You guys got any issues so far? Okay? You see the gist of what I'm doing. One variable. You got to get this in one variable. All right, what do you do now to finish this problem up? You do the derivative. Okay, so the derivative of this function is 64 minus 16x. Then what do? You set it equal to 0. So you have 64 minus 16x. Oh, 8. Okay. So 64 minus 8x. Like that. And then you solve this. So that's 8x equals 64. Divide by 8. That'll give x equals 8. So that's the dimension that you get there. Okay. Now what else do you got to do? Got to find y, because you're asked for the dimensions. Okay, so what you do is go back to this equation here that gave us y and do 64/3 minus 4/3 times 8. X is 8, so you want to go back and do that. So that's going to give y equals 64/3 minus 32/3. So that's y equals 32/3. So your dimensions are going to be this and this. So that would be your answer to what those dimensions are. So you would just say, and I guess this is in feet, so you would say 8 feet by, and you can leave that as 32/3 feet or change that to a mixed number if you want to, like that. Okay? Right? Is that on my answer key? Okay? Just making sure, because it's easy to make arithmetic mistakes when you're doing this. Let's do this next problem, then we'll take a break. So that's a pretty standard kind of thing, okay, for a final and just kind of an overview of optimization, okay? All right, let's look at this one. I also kind of like this type of optimization problem like this because it's pretty simple and straightforward. So what this problem says is you have numbers that have a difference of 2. There's an infinite number of numbers that are off by 2, right? You're going to find the ones that have a minimum product. So you're going to have 2 variables. So what you're saying is these 2 numbers, when subtracted, equal 2. That's what that says to me. The difference of 2 numbers is 2. All right? What are you minimizing? You're minimizing the product, so you're minimizing xy. Okay, like that. All right? Now, we got to put it together. Whatever we're minimizing, whatever we're optimizing is what we differentiate. So what do I need to do? Kind of like the last problem. This thing right here has to have one variable. So you decide which variable you want it to be. It doesn't matter. So I'm going to just move the y over here and get x. I'll get x is equal to y plus 2. Okay, where does that thing go? That's x, so it goes there. You always got to get this function down to one variable. Okay, I'm going to call this product. P is equal to xy. All right, so now I'm going to replace x with y plus 2. I'm going to leave the y alone, and I'm going to write that as p of y. Okay, then I can differentiate that. You can do it backwards too. You'll still get the same answer. Okay, everything okay so far? Okay, go ahead and multiply it out. So that's p over y equals y squared plus 2y. All right, you want to multiply that out. Now you want to do your derivative. P prime of y is going to be equal to 2y plus 2. Then what do? Critical point time. Okay, find a critical point. Set it to 0. Okay, solve the equation. That's 2y equals -2. Divide both sides by 2. That gives y equals -1. Okay, so that would be what one of the numbers is. Now, what else do you got to do? You've got to find x. Okay, so go back there. That's y, so that means x is equal to -1 plus 2. So x is equal to 1. Now notice we got real small numbers. We're minimizing something, so we got very small numbers. So the two numbers that are going to have a minimum product are going to turn out to be 1 and -1. Now see, notice the product of that's -1 too. So you've got a minimum when you do that then. Okay? All right, what's my answer key say? -1, 1. Okay? All right, just making sure. Okay, now I want to show you one other thing just real quick. Now you're done with the problem, but we have this thing, we haven't done much of this, the second derivative test. I just want to remind you of something. What's the derivative of 2y plus 2? 2. That means the second derivative is positive. What does that tell you about concavity? This, okay? Look at that, minimum. Okay, that's why I always think of the second derivative test verifies that that's a minimum. Okay, because of the concavity. Okay? All right, any good? That's about the level of my expectation on optimization is at that, okay? Okay, so let's break here for 10 minutes and on here. Now let's go over and see if we remember anything about logarithmic differentiation. So you're definitely going to see that. One problem, probably with logarithmic differentiation on it. So there's a certain process you go through. This problem right here, if you didn't do it by logarithmic differentiation, could be pretty challenging. I mean, because it's got a product of 3 things. I mean, you'd have to break it up into a product rule within a product rule, so you don't want to do it that way. So the first thing that you want to do on logarithmic differentiation is you want to make sure that this is solved for y, so that is solved for y, so we're going to take the natural logarithm of both sides of this equation then. So you want to start that way. Okay, and what we do is we take advantage of certain log properties. So you want to start by doing that. Okay, so you got to kind of go back to what you learned in college algebra. The key thing that hopefully you remember is if you have a logarithm of a product of 2 numbers, how do you break that up? Log of those 2 added, right? Log of a product is sum of logs. Now we've got 3 products here, so we're going to break it up into 3 logarithms. And you want to keep bringing this ln y down so that you don't forget about it. So we're going to have ln x to the 4th plus 1 to the 5th added to ln x minus 1 to the 4th added to ln of x to the 5th, like that. Okay, so you got that property. You've got to remember that property. All right. Now, what else do you remember about logarithms? What if you have ln of something like x to the n power? What do you do with the n? You bring it down. So you have to remember that property. Okay? All right. So what we're going to have is ln y, keep bringing it down, is equal to 5 times the ln of x to the 4th plus 1 plus, bring the 4 down, 4 ln x minus 1 plus, bring that down, 5 ln of x. Okay, you're not doing a derivative. I see students all the time on problems like this. They want to go 5 ln x to the 4th. Okay, you're not doing a derivative. You're doing a property of logs. Okay? All right, so far okay? All right, now we're ready to do calculus. I haven't even done any calculus yet, so we're going to differentiate both sides with respect to x. So what we're going to do, as we're doing this, we're going to really just do the derivative of ln of y. Okay, so what is the derivative of a logarithm? It's 1 over the function, but then you got to put in dy over dx like that. Okay, because you're doing a chain rule. So when you do this derivative, you're going to have 1 over y times dy over dx. That always works the same on logarithmic differentiation. You always have that, okay? Now what you're going to do is you're just going to do the derivative of each one of these things. Those are all logarithm derivatives, which are relatively easy to do. Okay? All right, so when we do this, what we're going to end up having is when you do this first derivative, bring the constant down. How do you do a logarithm derivative? It's 1 over the function times the derivative of the function. So go ahead and do that. So that's 1 over x to the fourth plus 1. Derivative of x to the fourth plus 1 is 4x to the third. Okay, so we have that. Move on to the next one. Write the constant 4 down. The derivative of ln of x minus 1 is 1 over x minus 1. The derivative of x minus 1, you don't have to do that because it's 1, but I'm going to put it in there. And then the derivative of 5 ln x is 5 times 1 over x like that. Okay, so that's what I've got so far. Okay, you guys got any questions so far? I haven't done this in a long time, so you definitely want to know how to do this. This kind of thing you do a little bit in calculus also, when Calc 2, when you do some certain types of derivatives. Okay, now we've done the derivative. We've got really a couple of more steps, and only a couple of more steps to do. So really what we're going to do is we're going to kind of clean this up, but we want to solve this equation for dy over dx. So what do we do to both sides? Multiply by y. You have to, so that y goes away. Then you substitute back in. Now see, y was this, so it substitutes back in. Now you can write the answer. You don't have to clean it up very much either. Okay, on this kind of a problem, you don't do a whole lot of simplification. So we're just going to write this as, when I put this together, write that as 20x to the third over x to the fourth plus 1. Write this just as 4 over x minus 1. Write this as 5 over x. Put a big bracket around it, don't forget that, and then substitute in for y, so you would have x to the fourth plus 1 to the fifth times x minus 1 to the fourth times x to the fifth, and you stop. Don't even waste your time going any further. You don't need to. That's it. Okay? Check my answer key to make sure. Okay, I think I did that right. I've kind of got off to a bad start, but making stupid arithmetic mistakes. Like 1 minus 0 is 0. I'm just making sure, okay? That look good? All right, very good. Okay, I'm going to do one more logarithmic differentiation. That's a pretty good standard example right there of the type of thing you do on this. Now, and I'll tell you that. That's the directions because I want you to show that you know how to do logarithmic differentiation. Any questions about that? The key thing is start by doing the log of both sides and use your properties. The reason we do logarithmic differentiation because it simplifies it. Okay, that's the idea. Okay, let's do one more of just kind of a different one on number 30. Now let's do that one together just for a little bit different example. Okay, so again, we're going to start by doing natural logarithm of both sides. So we're going to have ln y equals ln of x plus 10 to the x. Start that way, don't do anything else. All right, what can you do from here? Bring the x down, right? Okay, that's a property of logs. So we know if we have a log of like x to the n, we just bring that down. Keep bringing your ln y down. That's one thing that students are kind of bad about, and they forget about how you finish the problem up. So you're going to have x times ln x plus 10 like this, okay? All right, so we got that. Now we're ready to do our derivative of both sides, okay? So what we're doing again, and this will always work the same way, you're doing the derivative of ln y. What is that? 1 over y times dy over dx. That's one thing that students forget, okay? It's a chain rule. Those variables x and y don't match, so you do have to do that. All right, so let's write this as 1 over y times dy over dx. Now, let's focus on how we're going to differentiate this. How do you want me to differentiate that? That's a product rule, isn't it? X and ln. You have a product of two numbers, so you need to go ahead and get your product rule going on that now, okay? So we're going to do the first x times derivative of second. The derivative of ln x plus 10 is 1 over x plus 10. Derivative of x plus 10 is 1. You can leave that off. I'm just emphasizing that because you've got to use a chain rule. Okay, then we're going to do it backwards. We're going to do the second ln x plus 10, derivative of first, derivative of x is 1 like that. So I have now done my differentiation. Okay, so far okay? Now the product rule, this one's not going to be too bad algebraically. All right, so what we're going to do now, I'm going to just clean this up. I'll bring it up here. I've got 1 over y times dy over dx equals x over x plus 10 plus ln times x plus 10 like that. All right? All right, what else do I got to do? Multiply by y. Okay, got to do that. Don't forget that too. And so you got to have a bracket. That's another thing. I've seen some of you on gateway tests missing it because you don't have a bracket in the right place. That y is multiplied by everything, so you have to be careful about that. So then we're going to have dy over dx. We're ready to write our answer. So we have x over x plus 10 plus ln of x plus 10 and then times y. And then what do you do with the y at the end? Substitute back. Okay, remember that thing's going to go there, so you have to substitute back in. That's how you always close off the problem. So replace y with x plus 10 to the x. Doesn't matter if that's in the front of the brackets or at the end like that. So this would be your final answer. Okay? Right? So look okay? Okay, practice it and make sure you can do that. So that's kind of about the level that I'd be looking at on that. Those are two pretty good examples of logarithmic differentiation. Okay? Any questions? Okay, we're going to skip around because I'm finding what my experience shows as some of the problem areas, and we'll go back. I'm not doing derivatives so much yet because that's what you're doing on your gateway test. You're like studying derivatives a lot and getting that down your gateway. Let's go do a couple of implicit differentiation problems. So let's go down to number 33 and kind of see how this goes with implicit differentiation. We haven't done that in a while. So what you do on implicit differentiation, the reason we use this is this would be very complicated to solve for y. So what we're going to do is the derivative with respect to x of both sides of this equation to begin with then. Okay, so let's go ahead and get that set up. Okay, this kind of problem right here sometimes can get a little bit messy algebraically. There's a couple of details. This is a pretty standard example about the right level. All right, so let's just do this kind of one by one. What's the derivative of x to the third? 3x squared. The variables match, right? So that's okay, we're done. When you do this, what do you have to do? You have to do a product rule. Okay, you have x. You can think of 3x squared as the first and y as the second. So this thing right here, you got to use a product rule on. Okay, so do the first. The first is 3x squared. All right, what's the derivative of y? This is where you got to be careful. 1 dy over dx. So that's dy over dx. Okay, the variables don't match, so I'm just going to put in there dy over dx. I'll put that in red so that kind of pops out at us. Okay, first times derivative of second. Now I'm going to go second, which is y, times derivative of first, which is what? 6x. Okay, so that right there is the product rule that I've done. Okay, first derivative of second, second derivative of first. Okay, now we got the next one to do. What is going to be the derivative of y the third?
dy squared dy dx.
Good, you got to have that dy dx. Okay, good. That's the thing that you want to make sure you don't forget. So that's 3y squared times dy over dx. That dy over dx is popping up whenever you're differentiating y. And then the right side, of course, is going to be 0 like that. Okay, that's the details of the derivative. Okay, the rest of this is algebra. All right, so what you try to do on this is you've got to solve the equation for dy over dx. I'm going to draw a circle around these two things. They need to stay on this side of the equation. Don't move them. So let's just put together 3x squared times dy over dx plus 3y squared dy over dx, and then everything else you need to move to the other side because it doesn't have a dy over dx in it. So you're going to have negative 3x squared. This is 6xy, but you're going to move it to the other side so it becomes negative 6xy like that. Okay? Now, what do you do to the left side? Factor. Okay? A lot of times students forget that this is a common factor. And you have to solve for dy over dx, so you have to factor it out. So we're just going to say dy over dx, and we're going to take that common factor out, so you'll end up having 3x squared plus 3y squared equals negative 3x squared minus 6xy, like that. Okay? Then we're ready to finish it up. You can do this last step in your head if you want to, because what are you going to do in this last step? You're going to divide by this stuff right here so that dy over dx is by itself. So you'll end up having dy over dx equals this. Then we'll talk about if we have any simplification. I think we have just a couple of things that we want to simplify on this problem, because I do want you simplifying, okay, if that happens, okay? All right, so that's what it is. That's an unsimplified form of the derivative. So is there any questions about that? Okay, what can I do algebraically to clean this up a little bit? Factor, okay, we can factor a 3 out of the top and bottom. We can factor an x out of the top, so let's just factor whatever we can factor and do that. And you have a couple of options. Generally, if you have a negative in your first term, it's good to go ahead and factor that out. If you didn't, it wouldn't matter. But I'm going to, in the top, take out a 3x. I have an x in both positions. Then I'm going to figure out what's left. So I'm going to have negative 3x times x gives that. Then I have to have a plus. Negative 3 times 2 is going to give that. Then I have to have a y. So you got to factor that out. Now the bottom, we're going to factor a 3 out. And that would leave us with x squared plus y squared, like that. So then we'd have dy over dx. You can cross the 3's out. And you would have negative x times x plus 2y. You can just leave it in a factored form over x squared plus y squared, like that. I'll check my answer key and see if I got something either the same or mathematically equivalent. Do I have that? Okay. Do I have that in a factored form, or do they multiply it out? Okay. Okay. Doesn't matter, as long as it's mathematically equivalent. Okay. What do you think of that? Okay. I want to do a couple of implicit differentiation. These are sometimes problem areas if you don't follow everything exactly. Okay, of course, I get partial credit and stuff, but I want to try to be careful when you're doing that. Let's do one that's a little bit different implicitly. Let's do 34, so we have a couple of examples of how that goes. Okay, so what we're going to do, same thing on this. We're going to do the derivative of both sides of the equation to start with. And the key thing that you want to study is how that dy dx gets introduced in the problem. That's one of the areas where students mess up a lot. Okay, well, here's an exponential. When you do a derivative of e to a power in words, what do? Itself times derivative of exponent. That's the best way to learn that. So it's itself, but the derivative of the exponent is 3, like that. Okay, the more of these things you talk out in words, the better off you begin to get them. Okay, I don't need a dy over dx because the variables match. Okay, in general, what's the derivative of a sine of something? It's a cosine of something. I've seen some of you mess up on the gateway test on this. That's step 1. Take a deep breath and pause. Okay, it's the cosine of something. Now what? Now you got to do the derivative of what's inside. Now before we go jumping into that, let's just go ahead and write it out so we can focus on that the right way. Okay, that's a chain rule. Okay, so what we're going to have is we're going to have 3e to the 3x. That's equal to the cosine of x plus 3y. So that's all done. Now let's focus on this derivative, okay, which hopefully is pretty simple. Derivative of x is what? 1. Derivative of 3y is what? 3 times dy over dx. Okay, the variables don't match. Okay, so you're going to end up having 3 times dy over dx, like that. Okay, now that's your derivative, so I've got everything taken care of that I need to have so far before we solve for dy over dx. Any questions so far? Okay, now let's think about how we do this. Now we can get different kind of answers on this that are acceptable. One thing you can do on this is if you want to get rid of this whole thing right here, how do you get rid of that whole thing? Divide by it, exactly. Just do this in your head. Let's just do it that way. You could also do a distributive property if you want to, but we don't have to. So we could do it and just get 3e to the 3x over cosine of x plus 3y. Now that's going to leave us with 1 plus 3 dy over dx. Okay? Now again, the answer I get may not match with what they have. It doesn't matter. It should be mathematically equivalent. Now if I'm going to get this by itself, you can subtract 1. So you could write this as 3e to the 3x over cosine of x plus 3y minus 1 equals 3 dy over dx. So you can do that if you want to. All right, now, you're used to dividing by 3. It's better to not divide by 3. In this situation, it's better to multiply by a third. The whole thing by a third like that. Then you would have really a valid answer. There is a couple of things I'm going to do on this. But that will give you what dy over dx is. And then that would be an okay answer. I wouldn't fuss if you gave me that answer. What I'm going to kind of do on this is do a distributive property on this. And if I do a distributive property on this, if you look at this first term, aren't those 3's just going to cancel out? Okay, so you could write that first term as e to the 3x over cosine of x plus 3y. Then 1/3 times 1's minus 1/3. Now, I don't know if they have that answer, but that's acceptable. Tell me if they have that answer or something different. I wouldn't be surprised if they just got a common denominator and did that. Okay. I'm just curious what they have on that. Let me see what that is. You got that on there? This is what, number 35? 34?
Yeah, the sign.
Oh, they got a common denominator.
It says a sign in.
Yeah, they have 3e to the x over 3 sine x plus 3y.
I think they're wrong.
Yeah, they just have something like that.
Well, I don't know about that sign being there. I see the rest of it okay. That what they have done on this is, and you don't have to do this, but if you got a common denominator on this, you would have like e to the 3x over cosine of x plus 3y. You would have to multiply this really like this by 3 over 3, like this, and then this thing 1/3. I'll just bring that down and get a common denominator, so you'd have to multiply this by cosine of x plus 3y over cosine of x plus 3y. There, I can't see no way they got that sign in there. I suspect that's a problem on this unless they used an identity. So you could have 3e to the 3x minus cosine of x plus 3y all over 3 cosine of x plus 3y like that. I don't see any problem with that anywhere, so that all looks okay. I think I just, at this stage in the problem right here, I went about it in a different direction. One thing you could do is do a distributive property to solve for dy over dx, but I don't see any issue in that I've done. Everything looks okay there. Okay, yeah, I don't see anything on that. I think that one, I don't see what they've done on that one. I don't even see an identity on that, but you could stop this basically at that point if you wanted to right there anyway, okay? All right, so just tell me if there's anything that you have a question about with the algebra or anything on that, or the implicit. You can stop at that point if you want to like that. You could have taken that in a different direction. I don't even really see an identity on that for the sign. I'd have to think about that a little bit. Okay, so I'm going to do 36 next here. And on number 36, this is another one that's is a product rule that has a chain rule kind of embedded in it. So I want to go over this one a little bit. Okay, so this is a product rule. So this is going to be the first, and that's going to be the second like that. right? So what I'm going to do is write down the first. So that's going to be x plus 1/2 to the second, leave it alone, times the derivative of the second, x squared plus 1 to the negative 3. Then do it backwards, plus the second, okay, times the derivative of the first, like this. The thing on this problem that I always like to test students over this kind of problem because it tests algebra skills a little bit, particularly factoring. So set it up like this. Now what we're going to do is focus on doing this derivative and that derivative. And of course, those are chain rules. That's kind of an extension of the power rule. So you want to go ahead and do that. So this is going to be x plus 1 to the second. When we do this derivative, that's negative 3. X squared plus 1 stays alone. Subtract from the exponent, that's negative 4. Then what do you got to do? Derivative of what's inside is 2x. So it goes like that, okay? Now move on to the next thing. You have plus x squared plus 1 to the negative 3. This derivative's done the same way. Bring the 2 down. Leave the x plus 1 alone. Subtract from the exponent, but do the derivative of what's inside, like that. Okay, that is the calculus right there, okay? I kind of usually grade this about half and half. Calculus half, okay, if you got that, you're halfway done. Then I do grade the algebra because I want you to know how to finish the algebra. Okay, you guys see the derivative part okay? It's product rule, but chain rule embedded in it. Okay, now I'm going to do this. I'm going to write a step before I factor. I'm going to just sort of clean this up. So I have negative 3 times 2 is negative 6x. Then I'm going to write this as x plus 1 to the second times x squared plus 1 to the negative 4. Then I'm going to write this as 2 times x plus 1. I'm going to put a first there for emphasis. Then x squared plus 1 to the negative 3. One of the reasons I like this problem is because of the factoring. And I'm testing your factoring skill a little bit on that. Okay? All right, any questions so far? Okay, let's see what we have as a common factor. All right, so let's look at, well, first of all, we have a 6 and 2. We're going to take a 2 out. Now, let's take a negative 2 out because that's a negative 6. So let's start by taking a negative 2 out. Okay, what else do you see that's the same? X plus 1 to a power. Which one do you take out? The one to the second power or the first power? Smallest exponent. That's what you learned. Okay, so we want to do that. So we're going to take out x plus 1 to the first power. I'm going to put that in there for emphasis. Okay? Now, the other thing that's in common is this. Which one do you take out? Negative 4 or negative 3? Negative 4, the smallest. Negative 4 is the smallest. Okay? So you got to do that. So what we'll have then for this is we'll write down x squared plus 1 to the negative 3. Then draw your big bracket to complete your factoring. Okay? A lot of times Calc 1 students struggle with this because they have factoring background, but they've never seen it quite at this level, although you've taken common factors out plenty. Okay, so the way I look at this that kind of helps me is I'm going to figure out what I multiply this by to get what's in that box.
Would that be the negative 4?
Oh, 4. Yeah, I even said that, didn't I? Yeah, you take the smallest one out, thank you. Okay, so we got that. Okay, so what do you multiply negative 2 by to get negative 6? 3. You need an x. Put an x there. What do you multiply x plus 1 by to get x plus 1 to the second? X plus 1 to the first. Okay, like that. Make sure it's right. If you look at all that stuff right there, it checks. It's what's in that box. Okay? Then move on to the second one here. Okay, do this. All right, what do you multiply negative 2 by to get positive 2? Now, you got to change that sign, so it's minus now. Okay, you already have the x plus 1. They match. What do you multiply x squared plus 1 by so that it becomes negative 3?
X squared plus 1.
The first, okay, right? Negative 4 plus 1 is 3. All right, okay. So notice if you do that, negative 2 times negative is positive 2. You already have the x plus 1. And then this times this, negative 4 plus 1 is 3. That's the factoring. For most students, that's the hardest part of the problem right there. Okay? You see what I've done? Okay? The negative exponent might be bothering some of you too. You got to look at that. Okay, so write your answer now. You got negative 2, x plus 1, x squared plus 1 to the negative 4. Then you want to go ahead and multiply this out, see? So inside the parenthesis, you're going to have 3x squared plus 3x. Distribute the negative, so that's minus x squared minus 1 like that. Collect like terms and then done. I suspect of the answer key they may have made the negative exponent positive or something. So I have negative 2, x plus 1, x squared plus 1 to the negative 4, and then this is 2x squared plus 3x minus 1 like that. Okay? I'd leave it there. I mean, you could bring that negative exponent down too if you wanted to, and I suspect that's what I did on the answer key that I took it from the computer. Yeah, okay, that's what they got. They just took that negative exponent down, but you don't have to do that. Okay, does that factoring make sense? Okay, how do you check something when you factor it? You multiply it out. Okay, you make sure the exponents add the way they're supposed to. You don't leave it up to guesswork, you verify it. Okay? So that's something that's an absolute that's always a final exam problem because it's testing that factoring skill. Okay, now let me move on. Let's kind of continue to go backwards with this. Now I'm going to go probably back to difference quotient because there will be one difference quotient. You're like, oh God, why are you testing me over the difference quotient? Well, that's where all derivatives come from. So there's one problem where I want you to know how to do a difference quotient, okay? And something pretty straightforward. All right, so the difference quotient, the definition of a derivative, let's go to this number 43. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. I don't give you that difference quotient. You're a calculus student. You got to know it. Okay, I know we haven't done that in a long time. But the nice thing about this problem is you're going to know what the answer is, right? So if your difference quotient is not giving you, you now know, of course, the easy way to do the derivative, which is 12x plus 5. If you aren't getting that, then you need to go back and figure out what you did wrong. Okay, you know the answer. Okay, so let's go ahead and put this together then. All right, so it goes like this. I always tell students when you formulate this difference quotient, just kind of set up the framework kind of like this. Just put a bracket there, put a bracket there. It becomes mostly an algebra exercise, okay? All right, so f of x is this. F of x goes in the second bracket. Okay, so that's going to be 6x squared plus 5x like that, okay? Now, what's the difference between the function I gave you and f of x plus h? What's the only difference? The x's get replaced with x plus h. Okay, so I'm going to do this like this. Over here, I'm just going to put 6, then x plus h to the second, plus 5 times x plus h. That's the only difference. Okay, if you look at that very carefully, everything's the same except for that one change. Okay, that's how that goes. All right, so now what we need to do is just kind of crunch out some of the details on this. So we're going to have the limit as h goes to 0. We're going to go ahead and multiply all this stuff out. Okay, if you don't know how to do x plus h to the second in your head, go to the side of your paper and FOIL it. What the answer is it's x squared plus 2xh plus h to the second. Okay, and you all can do that if you have to, either in your head or FOIL it. Then do this, so that's going to be 5x plus 5h. Distribute the negative through the parentheses to get negative 6x squared minus 5x, and then all over h like that. Okay, so it's all just an algebra exercise. Once you get everything built, then you should be able to do the algebra. Now, I would hope a Calc 1 student by the end of the semester has hardly any issues with this whatsoever. Okay, it's okay to have that at the beginning of the semester, but you need to have this down pat by now. Okay, so that's going to be 6x squared plus 12xh plus 6h squared plus 5x plus 5h minus 6x squared minus 5x all over h. Okay, now remember, what happens on these problems is a bunch of things cancel, right? Go ahead and cancel everything that cancels. 6x squareds cancel, that cancels, and that cancels. And what you're going to notice on this, everything that's left has an h in it. So what do you try to do to finish this problem up? Factor the h out, cancel it, then you can evaluate your limit. Okay, like that. So what you'd end up having next is you'd have limit as h goes to 0, factor the h out of the numerator. So you have h times 12x plus 6h plus 5 all over h, like that. Okay? Now plug in, evaluate your limit. So replace h with 0, so you get 12x plus 6 times 0 plus 5. That's what we expected to get, right? So that's what the derivative is. Okay? All right, that's a pretty good standard, like a quadratic, nothing real complicated, just something to make sure that you remember how to do a difference quotient. Now, the other thing this problem said is it said find f prime of 4. So what we found is f prime of x, by the definition of a derivative, is 12x plus 5. So f prime of 4 just means you replace the x with 4. So you're going to get 12 times 4 plus 5. So that's 48 plus 5. So that's what, 53 should be the answer on that then. Okay? Okay? So I definitely wanted to do that. You want to practice something that's got a fraction in it like that, where you had a complex fraction in. We did that earlier in the semester. So I kind of look at quadratic or something maybe with a fraction. Okay, do you guys remember that? Do you remember your formula? Okay, that's the difference quotient, because I don't give you the difference quotient. If I say use the difference quotient to find a derivative, you got to do it. You have to show all those steps, although you're going to know what the answer is, see. Okay? All right, now let's move down to going back to doing some limits from a graph. And remember, before we learned L'Hopital's rule, we just evaluated limits for the most part. Now, you can use L'Hopital's rule anywhere you want to, as long as it's a 0, 0 or infinity over infinity. But I want to remind you sometimes is if you start, you always want to start a limit just by plugging in and seeing what happens. So on this one, you would have 6 plus 6 over 6 minus 6 squared. That's 12 over 0 squared. That's 12 over 0. Can you use L'Hopital's rule? No. What's the answer to this problem? Does not exist. That's an example of a limit that doesn't exist. Okay, if you end up with a constant over 0, you've got an asymptote on that problem. The basic idea is that's a rational function, so you have an asymptote. So that's going to mean that you're not going to have a limit at that value, because it's probably going to be approaching different directions when you do that. And something like this 45, this is just kind of going back to when we started learning limits. You just start by plugging it in, and then you see what happens. Sometimes you just do arithmetic and you're done. So that one would be 2 over square root of 4 plus 2. So that's going to be 2 over 2 plus 2. So that's 2/4, so that's a half. Those two problems right there are just straightforward limits that you evaluate on. Okay, and if they are situations when you can use L'Hopital's rule back on the things we learned way back in the past, you can certainly do that. Okay, all right. Now, one of the other things that we want to look at is going back to what we did in the first chapter we learned is graphs and limits. Okay, so if you went back to your first exam, I give you a graph, you work all the limits out. Okay, so we're going to want to go through and review that. We hadn't done this in a long time. So let's go through some of these things. Okay, this is a, let me zoom on this a little bit so I can see that a little bit better. Okay, this is a left-hand limit. Okay, so if you're doing the limit as x approaches 0 from the left side, remember what you do is you get to the left of where x is 0 and you close in on it. Okay, is it going somewhere? It's getting close to 0. It doesn't jump up there. It's only where the function is you're just as close to 0 from the left side as you can possibly get. So that's 0. That's a left-hand limit. Okay. if you've got part B, you now have what appears to be a right-hand limit. Okay, so what you do on this is you get to the right of this, you get to the right of 0, and you close in this way. So where are you going on that one? Going to 2. So we got that. Okay, all right. Now, if you go to, what's the next one? So I can't even read that. Does that say 0? Yeah, okay, that's what that makes sense. Okay, all right. So now what we're doing on this is we're closing in this way, and we're closing in this way because that's a two-sided limit. Do they come to the same place? No. So what do we say? Does not exist. Okay, they don't come together, so that one doesn't exist. So I wanted to try to go through all the little details we saw. Okay, let's see what happens on this next one here. So this is a left-hand limit at -2. So we're kind of interested at -2. If you go to the left, where are you going? -2, good. If you're going from the right, where are you going? 0. Okay, like that. So what is the two-sided limit then? That does not exist. Okay, you're not going the same direction. You guys remember that? Went way back in the past when we did that. Okay, now I have no idea. Does that say 4?
Yeah.
Okay. Okay, so if we go to 4, and this is kind of a good one right here. This is another situation. So this is a left-hand limit. So if you're going in towards the 4, where are you going? Going to 4. Okay, that's from the left. This is a right-hand limit. So now you're going from the right. Where are you going? 4. What's the two-sided limit? 4. It's okay that it has a bubble. Okay, it only matters that they're coming together. Okay, as long as they're both left and right are coming together, then that limit's going to exist. You guys remember that? Okay. All right. Let's do a few more of these limits. Okay, 'cause I want to try to just make sure we've got all the different cases going here. And then after that, I'm just going to have you guys look at this, and we'll kind of look over just a few last things here. Okay, so let's look at this. These are when limits can go to infinity. So this one you're looking at, x approaches 1 from the left-hand side. So that means you're going to go like this. You're to the left of 1. Where's the graph going? I think I made my point. Okay, that one's going to infinity, right? Okay. All right, the next one is x is going to 1 from the right. So where's that one going? Okay, infinity also. Okay, so they can go to infinity. You can do that. Okay, now this is the two-sided limit. Are they going to the same place? Okay, yeah, they're both going to infinity. So you can put infinity on that. They're both going in the same direction. Now, if one was going to positive infinity and negative infinity, what would you say? Then it doesn't exist. Okay, all right, and then this one is x approaches 2 from the left. Okay, so we're going to go this way. All right, now this is probably what this is saying. So to the left of the asymptote, you're going where? Okay, so this one's going to infinity. Okay, if you're going on the right hand on the next one, where are you going? Going to negative infinity. So what would be the two-sided limit? Doesn't exist. Okay, you're going there, and then you're going to negative infinity, so that one does not exist. Okay, you guys got that? Remember that? Those are all the different things that we looked at. I want to just do one more thing, because what this is these are limits that go to infinity, and then we also learned about limits at infinity. So all of these are, or at least a couple of these, are limits on this, and I can hardly see this one. I know that says limit as x goes to infinity of f of x. Okay? So if you're doing an infinite limit, you're just seeing what is the graph doing as x gets bigger. Where's this graph going? It's getting higher and higher forever. Okay, it's getting infinitely high. That always sounds funny when I say that to me. Because I live in Colorado. Okay, so the next thing is we've got, what does this one say? Limit of x goes to -1, okay, of f of x. Okay, so if you're going to -1, and this is actually a two-sided limit right here. Now, is this, what is that -1 right?
I think it's supposed to be where that.
It's like in between, right there.
Like there probably? Okay, because I can't see those numbers. Okay. Okay, it's a two-sided limit. Here's -1. So this one, the right-hand limit's going to infinity. Left hand's going to infinity, so what do we say? Does not exist. Okay, so we got that. And then the next one is limit. X goes to 1 from the left side, so that would be, now that's a +1, so I guess that's supposed to be there. So if you're going to 1 from the left side, where are you going? Okay, going to -infinity, it looks like. Okay, and then the next one is limit X goes to 1 from the right side. So here's 1. Going from the right side, you're going to +infinity. Okay, like that. Then the last one, does that say X approaches what? Infinity again?
The first one was negative.
Oh, the first one was -infinity, wasn't it? Okay, so yeah, okay, let's correct that then. This number 1 was -infinity. So as you're going to -infinity, where are you going? -infinity. Now if you're going to +infinity, then you're going to, the limit's going to +infinity like that. Okay? All right, so that's another thing that you want to know how to do. Is just basic, being able to look at a graph and interpret the limits and all the different ways that we've learned. Okay? Okay, let's kind of back up here, and a lot of the things I left off were things with derivatives. I did some. We've done a lot of integrals today and everything. So we did. I want you to just kind of look on this and see. Here's extrema. There's the increase decrease. Anything I do on increase decrease, since you're not allowed to use a calculator, pretty straightforward polynomials that don't have very difficult arithmetic. I have you usually do like you did on the last test, where you have some statement, you draw a possible graph. I have lots of derivatives, obviously, so there's a bunch of derivatives on here kind of built in. Find where functions are discontinuous, find where functions are differentiable from the graph. You guys remember all that? Okay, how are you not differentiable? What do you look for on a graph? A break, what else? Cusp, sharp point, okay, like that. Okay, and then I think I got a few things on concavity in here. And lots of derivatives. Of course, the answer key is on here and everything. So there's anything on here that just, I mean, I can do another integral or two if you want me to. If there's anything on here that you want to glance through and look at, then let me know and we can finish up class that way. Usually that means everybody wants to go. All right. All right. Oh, he's messing us up. Thank you so much. Okay, thank you, man, Jira. They're gonna maybe mug you outside of class. What did you say? I'm sorry.
23.
Okay, 23. Thank you. Okay. Yeah, and this is about the level that you would do on this. Now we're doing increase decrease. So you want to start by doing the first derivative. So this is 4x to the third minus 16x. So this is one you do a sign chart on. So the next thing is you want to find your critical points. So you have 4x to the third minus 16x. And you got to solve that by factoring. The best thing to do here is probably divide by 4. So that's going to be 0 is equal to x to the third minus 4x. Okay, then we can factor an x out. So that's x times x squared minus 4. Okay, I would go ahead and factor the difference of two squares is x plus 2x minus 4. Now, see, you have to have your factoring down or you don't get anywhere on a problem like this. Now, the algebra issue is you got to be able to factor and you got to factor well. Okay, now, what are your critical points based on that factoring step? 0, negative 2, and 2. Okay, so you're going to have critical points at 0, negative 2, and 2. You're not going to have a calculator, so you need to make a sign chart. Again, since you're not going to have a calculator, I tried to make the polynomials fairly simple with arithmetic. So you go ahead and just do this. You do 0, you do 2, and then you do -2. And then you analyze the derivative. The easiest way to analyze the signs of the derivative is to analyze the factored form like that. Okay? All right, so let's do that. You don't really have to show any work on this, so let's take a test point like, say, -3. And see, you can do this like this. That's -3 there, so that's a negative. If you plug -3 in there, you have a -3 plus 2 is negative. If you plug -3 in there, you have a negative. So what's the result? Negative. Okay, what does that tell you? Function decreases, right? Negative derivative, function's going to decrease. Okay. Then I just kind of go back, and you can do most of this sign arithmetic in your head. So let's use -1 as this test point. So let's put -1 there, -1 there, -1 there. So you're going to have negative times positive times negative. So what's that? Positive. Function increases. Okay. Then go in and put another test point. Just kind of keep doing that to fill this in. The signs don't have to alternate. You got to crunch it out to make sure that you know that. So this one you would have positive times negative. So that's negative. So that means you're decreasing. And then the last one, if you put like a test point like, say, 3 in, that you're going to get positive. So it's positive, so you're increasing. Okay, you guys remember the sign chart? I did that very fast. Okay, that's sometimes students don't do that right. So the other thing that I do on these sign charts is I box in my test points. So when I write my answer, I don't use my test points to write my interval, because I see students do that all the time. So now we're ready to write all of the answers to the problem. So increasing means we're going to be increasing in these two places right there. Just write those in intervals. Now, whenever you're doing increasing and decreasing, they're always open intervals. So you're going to say -2 to 0, union 2 to infinity. We don't use brackets or anything. They're open intervals. Okay, decreasing is going to be what I'm shading in the yellow there. So that's going to end up being -infinity to -2, union 0 to 2, like that. Okay? Now, you got no calculator. So the way I figure out max and min, this is what I always do on this problem, is I just kind of look at this like this. I just draw a picture over my sign chart. What am I doing? I'm decreasing. Then what am I going to do? I'm going to increase. Then what am I going to do? Decrease. See, the sign chart tells you a lot about how the graph behaves. So how many minimums do you have? 2. And all I'm wanting is the x values to save you some arithmetic. So we'd say -2 and 2. So I say x equals, so you put -2 and 2. And then the max is at 0 like that. Okay? A lot of times, like on the test that you did last week, a lot of you messed up because I said point and you didn't put a point there. Okay? Or I said x equals and you gave a point. Okay? So pay attention to that. The reason I probably wouldn't have you give a point on this is just because it's arithmetic. It's kind of a hassle to go through, plug it back into the function and work out. So if you've identified it that way, then you can do that. Okay? When you do concavity, what's the only difference between this problem? If I had you do concavity, what would you do? You go to the second derivative and make a new sign chart. Okay, like that. Okay. Yes?
The point of inflection is where the concavity changes?
Exactly. Now, point of inflection, if I say point, you're going to have to give me the point, but I might also say point of inflection at x equals something. Okay? But remember that it has to be a point on the graph. Let's see, one thing that sometimes happens on concavity is you might have something like this. You might have like an asymptote. You might be concave up and concave down. Well, the concavity changed, but that's not a point of inflection because it's not a point. You got to have something like this. Okay, you got to have a point on the graph, and it's a point where the concavity changes. That's what that is, okay? All right, study hard. And please come